right, let's get started. Good afternoon, everyone. My name is Susan Perkins. I am the Martin and Michelle Cohen Dean of Science at City College of New York. It is my great pleasure to welcome all of you to today's Division of Science Distinguished Alumni Award presentation. Recently, I celebrated my one-year anniversary of being at City College. Part of my attraction to the institution and to the Division of Science in particular is its rich history of successful and noteworthy alumni. In fact, 11 of our graduates have gone on to become Nobel Prize winners, including today's honoree. But also a major attraction is the role that City College plays in being a continuing force in propelling students from New York and beyond, many of whom are first-generation students, into rewarding careers. This mobility engine, as it is often called, is a complex machine that involves our faculty, our staff, our infrastructure, and all of our students, current and former. These parts work together to provide experiences that are mutually beneficial to all. We learn from each other, we grow with each other, we lift each other up, and we celebrate our accomplishments and successes. So today we are continuing this new tradition in celebrating the successes of the graduates of the Division of Science who have taken their knowledge, their hard work, and their desire to make their communities, their countries, and this planet a better place. We are proud to celebrate Dr. David Rind today for his successful career and how proud he has made his alma mater. A graduate of City College in 1969, where there was a Department of Meteorology, Dr. Rind went on to a PhD at Columbia University and a career at NASA that so far has spanned 4 decades. He was among the group of scientists who produced the Intergovernmental Climate Change Report, for which they jointly received the Nobel Peace Prize in 2007. You'll soon hear more about Dr. Rind and his trajectory soon from the Chair of Earth and Atmospheric Sciences, Dr. Pengfei Zhang. Before I turn the mic or the screen over, I have a few people to thank. So the Dean's office staff, as always, has been incredibly helpful as we put this event together. Laurent Mars, Elizabeth Rudolph, Sydney Gonzalez, and Frank Pace in particular. I want to also again thank Joanne Huang in communications and Anthony Achille for their help with the award and setting this webinar up. And I want to thank those of you who contributed donations to support this event. We very much appreciate your generosity in doing that. The final person I need to thank in helping out with this is David Covington, who is the Executive Director of the City College Alumni Association, who's been so supportive of these awards. And I'm going to ask him to just say a few words now as well.
Hi, Susan. Thank you so much. Good afternoon, everyone. Thank you, Dean Perkins. And first, I want to congratulate you, Dr. Rind. As I mentioned to you earlier, your career is extremely impressive, and it would be impressive by any measure, all the more impressive with your work on the Intergovernmental Panel on Climate Change. I'm excited to hear your talk today, and in particular to hear some of your advice to students and recent graduates pursuing a career in climate modeling. I'll be brief. I have the distinct honor, as Susan mentioned, of serving as Executive Director for the Alumni Association for the City College of New York. And Dean Perkins, actually, we have a similar anniversary date. I just passed my 2 years here at the Alumni Association. The association can trace its origin to the first graduating class. July 26th, 1853 was when members of that class met in the chapel of the original building on 23rd Street. They formed the Associate Alumni of the Free Academy. And through the years, it's grown, of course, incorporated, changed names. Today, the association has 15 local affiliate groups and 10 active chapters around the country. One of those affiliate groups is the Science Alumni Affiliate Group. We're currently looking for members to serve on their board. So if you're interested, please inquire with me and or our office. After I speak, I'll put my contact information in the chat. The mission for the association is trifold, right? To generate and sustain meaningful connections with alumni, to support current students, and to promote this great college. If you're an alumnus and not already a member, or if you just want to learn more about us, our oral history project, our alumni recognition awards, such as the Townsend Harris Medal, please check out our website, ccnyalumni.org. By providing opportunities for alumni to reminisce, volunteer, connect, come back and speak, pay it forward. The association ensures, as it has for 168 years, this cycle continues, that a new generation of hardworking, grateful City College graduates will go out into New York City, the nation, and even the world and change it for the better, such as Dr. Rind has done. We'll hear about now. So in you, Dr. Rind, your alma mater has particular reason to be proud. I'll hand it back to you, Dean Perkins. Thanks so much.
Thanks so much, David. I also just want to thank all of you who are in the audience today. I know these webinars are not exactly the warm celebratory things that we would like. We wish we were doing this in person, but we're really glad that you're able to join in today's presentation. We are recording it, and soon we will be able to post the recording. We do closed caption it, and as you might imagine with a scientific talk, sometimes the automatic translation doesn't do a perfect job. So we do take a couple days to go in and hone that. I just wanted to say, maybe this is a little silly, but I thought we scheduled this event, even though we didn't know ahead of time, really during the perfect week. We're about to honor a graduate with a BS in meteorology during a week when we were all obsessively watching the weather very carefully with that massive storm that we got and threats of one coming. And then yesterday again, when we saw our small mammalian meteorologists, the groundhogs, predicting or not the arrival of spring using their sophisticated shadowy ways. So on that note, let me turn it over now to Dr. Pengfei Zhang, who's professor and chair of the Department of Earth and Atmospheric Sciences, who will take over presenting today's Distinguished Alumni Award.
Thanks, Dean Perkins. Good afternoon, everyone. It is my great honor to introduce you our distinguished alumnus, Dr. David Rind. Dr. Rind received his bachelor's degree from this department in 1969, his master's degree from Columbia University in 1971, and his doctoral degree also from Columbia in 1976. He has been with NASA's Goddard Institute for Space Studies, or the so-called GISS, for the last 40 years. He was also an adjunct professor at Columbia University for over 30 years. Dr. Rind's research interests include climate modeling, climate dynamics, and climate change, paleoclimate, hydrology, remote sensing, among others. He has published hundreds of peer-reviewed papers with over 50,000 citations, according to Google Scholar. Dr. Rind is a fellow of the American Geophysical Union and a member of the Intergovernmental Panel on Climate Change, IPCC, which received the Nobel Peace Prize in 2007, as Dean Perkins just mentioned. He is the recipient of numerous prestigious awards from NASA, American Meteorology Association, American Geophysical Union, etc., and the Watt Medal from this department, which we still give out to our best graduating seniors today. I actually was a bit surprised to see that Dr. Rind listed this little award together with his Nobel Peace Prize on his CV. I guess this small detail kind of reflects his humble personality and his gratitude towards CCNY and this department. Here I quote from a retired EAS meteorology professor, Dr. Stan Genzelman. Always humble, David's accomplishments in the field and the breadth of knowledge are and have been sterling. He is most deserving of an outstanding alumni award, unquote. Dr. Rind's work has inspired generations of young scientists to pursue a career in the field of climate science. Our very own faculty, Professor Johnny Luo, is one of them. So I'm gonna turn the microphone to Johnny. Let him share some of his stories on the influence of Dr. Rind on his career. Johnny?
Thank you. Well, David, congratulations. As one of your former graduate students at Columbia University, I want to join everyone else to congratulate you on this day. But I also, on a personal level, I want to thank you for inspiring me during my graduate years and beyond. Probably you don't know it, but your influence on my career life is enormous. I still remember taking your classes back in the late 1990s. In 1998, I took your climate dynamics class, which is based on Dennis Hartman's book, and then the year after, 1999, we went on to Jim Houghton's book, The Dynamic Meteorology. I remember all the details. The reason I remember these things is, is that many years after I came to City College, I've been teaching these classes. Even right now, I'm teaching the climate dynamics, which is modeled after your class back in 1998 I took. So that's really, it's heartwarming to think that the torch has been passed on from you, then to me, and then to City College. I really want to say thank you. I look forward very much to attending your lecture again today after many years. So without further ado, we're going to hear Dr. Rind's seminar entitled "A Career in Climate Modeling, Climate Change Research." David.
Well, thank you, Johnny, and thank you, Dr. Susan Perkins and Fei Zhang and everybody else who was involved in providing me with this distinguished alumni award. And also thanks to all of you who are attending this seminar. I'll start sharing my screen and we'll see where it goes from here. So can you all see this?
Yes.
Okay. And let's see if we can. Okay, so I was asked to review my most significant accomplishments and discuss how my time at CCNY influenced them, and they definitely did influence them. The title of this presentation, as you can see, is A Career in Climate Modeling, Climate Change Research, which I think embodies whatever I've been able to accomplish. I thought you might be interested in how one goes about developing climate models, which will often also give me the opportunity to indicate exactly how my studies at CCNY contributed. And this will also involve a discussion of climate change, its uncertainties, and some of the work we've done to contribute to it. I realize those attending this webinar may have potentially a wide variety of backgrounds, so don't worry about the scientific details on some of the figures. I'll point out what I think is the main idea, hopefully clearly. Okay, so as was noted, I graduated from CCNY with a BS specializing in meteorology in 1969. Took about 10 undergraduate classes in meteorology in what was then 7 in the geology department, in which there was a very distinct meteorology department, and 3 that were actually given in the physics department. As was noted, received a PhD from Columbia in 1976, and I started working at NASA in 1978 to help build a climate model, and I'm still there now as an emeritus. And again, as was also noted, I was an adjunct professor at Columbia for some 30 years. Some of the other things have already been mentioned, including the various publications. And a bit about the work, specialized in building and utilization of global climate models for understanding climate change and atmospheric dynamics. And I list here one of the latest articles that was published earlier last year, again about building a climate model, in this case, climate model going up through the middle atmosphere, which is the region above the troposphere. Also, I've been a member of teams utilizing and building satellite instruments, the most prominent of which was SAGE-2, which monitored volcanic aerosols, ozone, and water vapor for some 20 years. And finally, looking at the impact on society, have been involved in helping to evaluate the impacts of climate change on various aspects of the natural world and society. Okay, so let's start off with what is a climate model? It's a numerical model built around the so-called Newtonian conservation equations for energy, momentum, and mass, as well as the conservation equation for water vapor. So in that respect, outside of the water vapor component, it's sort of like a lot of other physics disciplines. Many thousands of lines of code in a model, and they run on fast supercomputers. And the idea is that the Earth is broken down into grid boxes that cover the planet and layers that represent the vertical structure of the atmosphere. And in this picture, you can actually see the little grid boxes here. The Earth is being broken down into these grid boxes. And each grid box contains a lot of different things, which we'll get to in just a moment. We have to include all the various components that can affect the climate. So in that respect, it differs from weather forecasting models whose main focus is on short-term changes. Also, weather forecasting models have much finer grids. That grid we see, those little grids, are much finer in weather forecasting models. You can't really afford very fine grids in climate models with our current computing capacity because these models have to run hundreds of years. Weather forecasting models run, a couple weeks. Okay, so what's in each of these grids? Imagine, let's take a somewhat supercilious example. Let's say a grid was Riverside Park down near the Hudson River. Well, if you had to model and include in your model everything that's in that particular grid, what would be in there? Well, for one thing, as far as climate goes, you'd have to have something coming from the sun. You look up, there's the sun. You have the energy from the sun coming in, and realize that that energy does everything. It generates weather, it generates climate. So that sun's energy is going to have to come in, and some of it is going to have to be absorbed in the river, or if it was near the sea, near the ocean. So you have to have an ocean model, and the ocean moves, so it's got to be a dynamic model like the atmosphere moves. You'd also need to have river basins. In Riverside Park, there are areas that are vegetated. The sun is hitting that vegetation, so you have to have a vegetation model. The sun can hit the bare ground. Some of the energy can go into the soils, so you have to have a ground model. There may be clouds around, so you have to have a cloud model. And the other component that is of main interest to people about the climate is the weather, and in particular, the precipitation that falls, like the snow we just got, or rain. So you have to have a hydrologic cycle. You have to be able to evaporate moisture from the ocean or from the river. You have to have it rain. Some of that rain will fall on the vegetation. Some of it will fall on the ground and infiltrate into the ground. And when it's in the ground, the vegetation will be pulling it back up. Some of the energy in the earth will be emitted back into the atmosphere. So you have to have species in the atmosphere that may be able to grab it. So all of these different components have to be modeled in these particular grids. And then the grids will have an atmosphere above them broken into different layers. So that, in one sort of slide, is all the things you need to include in a climate model. Well, why do we need such models? First of all, the system is too complicated to understand analytically via equations. And my little warning here is be wary of simple models. And I like this quote by H.L. Mencken. For every complex problem, there is an answer that is clear, simple, and wrong. And in the climate system, we have a number of such models without picking out names. So we need a model that actually includes all the complexity of the system, at least the complexity that we know about. The model can help provide information that we can't see well today. For example, winds out over the ocean, a number of tropical processes. It can help us depict and understand past climate variations, such as ice ages and the warm climates before those, and can also potentially help us predict future climate changes, in this case now associated with global warming. So perhaps help us adapt to them and or mitigate them. Well, how does one, so let's say you've gone to the problem of developing such a model. How do you test it? Well, first of all, it should be able to reproduce the current average climate with a reasonable degree of accuracy. And you can see quotation marks around several of those terms there, because how well do we actually know the current climate and what does reasonable mean in this regard? And there's a lot of flexibility in both of those terms. Also, we need to reproduce the current variability and the processes responsible for it. You may know that you've often heard the term La Niñas or El Niños, sea surface temperature variations in the tropical Eastern Pacific. Well, your model should be able to produce that. Storms have different tracks. They go different places. In some seasons, one place, some seasons, another. The model should be able to produce storm tracks. Various different components of variability. Also, we now know that over the last century, the climate has been changing. We have to see whether the model can reproduce anything like the current changes that we've seen. And in order to have it do that, we have to know what has been forcing those changes. So the model has to be given or generate its own climate forcings and produce appropriate trends. And finally, we would like to know, since the future climate may be quite different, how well does the model do on past climates that were quite different? Ice ages, and again, very warm climates. So let's look very quickly at each of these four aspects. Reproducing the current climate, mean conditions. On the left, there are about 28 different climate models now. They're not all distinctly different. Some are variations of a given model. But nevertheless, this is the multi-model mean surface temperature. You can see the bar on the bottom indicating those temperatures. And appropriately enough, it's warm in the tropics and cold at high latitudes. On the right-hand side, this is from IPCC 2013, you see the multi-model mean bias. So the models tend to be a little bit too warm around the Southern Ocean region, a little bit too cold in the Northeast, North Atlantic. I mean, these are small temperature deviations, but they are real. And so this indicates the models in terms of ability to reproduce the current temperature is quite good, but not perfect. You also see regions in the Eastern tropical Atlantic and Pacific that, at least at this point, were too warm. How about rainfall? Rainfall is much tougher for models to get. This is the model multi-mean precipitation. And again, it looks pretty reasonable. It has rainfall in the tropical regions and the so-called intertropical convergence zones. It has dry deserts, somewhat dry deserts, and dry regions in the Eastern tropical oceans. Here is the multi-model mean bias. And you can see the models tend to rain too much in the tropics. And in this case, on average, they're too dry in the Amazon. So the bottom line here is the models are not perfect, but they do a reasonable enough job. And I can say this, when I first started in the field, the models were a whole lot worse. And in particular, because you need an ocean model as well. Ocean models, when I started, were sort of babies crawling around on the ground. They couldn't produce proper temperatures at high latitudes. Their tropics were way too warm. Now, the deviations you see in temperature in the oceans are not bad compared to what they were initially. So we definitely have improved. How about variability? Well, this is just one example from a paper we published earlier this year. What I'm showing here is the density of storm tracks. And to orient you, this is the Atlantic, this is the Pacific, this is North America. The red indicates the regions where you get a lot of storms. And the right-hand picture here are the observed. A lot of storms in the Pacific, a lot in the Atlantic, along the coast, North America, some storms over North America. And so this is what you would try to produce. The earlier version of our NASA model, GIST model, this was its storm track, way too weak in the Pacific. And notice over land, over North America, very little in the way of storms. The model that we just published did not have this as its prime focus, but it ended up doing better over the Pacific. Though you can see even further south, there are not enough storms. They don't move far enough south. And it does better over North America, but not as good as in the real world. The reason that most people would think for these deficiencies are that to actually get storms right, you need to have those grids be very fine resolution. The National Weather Service, when it has forecasts, is using grids of about 1/4 degree, or even in some cases higher latitude and longitude. These grids were 2-degree resolution, and climate models now are running with at best for these long runs 1 degree. This is not really good enough to get storms in all of their entirety. But computer processing is getting better, and eventually models will get good enough, just not quite there yet. How about reproducing observed trends? Well, this is now going from 1890 to 2020, and this is the so-called global mean annual average temperature anomaly. So this is relative to a specific time period. Back in 1870, you had temperatures here. The black line is the observations. And you can see starting from about 1970, that black line's going up. The total warming as of a little over past 2010 was on the order of about 0.7 of a degree warming since 1880. But most of that has been from 1970 on. You also see here volcanoes that went off, and they produce localized cooling, as we'll discuss in just a moment. The other curves on this picture are curves associated with the different models. What did they do for their temperature changes over this time frame? And the red curve indicates the model average, which you can see is actually not bad compared to what happened. Now, we have to recognize that modelers, when they produce their models, know what happened. And one might suspect that if the model does a terrible job on what actually happened over the 1900s, that model will be fixed. So this is, in a way, models that have already been fixed to some degree. But nevertheless, with those fixes in place, they do a pretty good job on getting the trend, at least so far. NASA has just released an updated temperature assessment, as has NOAA and ECMWF and European models, as to what actually has happened now up through 2020 in terms of the observed temperature. And you can see that from 2010 on, the temperature has continued to warm. And now the thinking is that global mean temperatures increased about 1.1 degree centigrade. Again, most of it since 1970. So that's temperature. A more complicated process in particular has to do with things like Arctic sea ice. On this picture, you see the observed sea ice in the light blue color as a function of year from 80 through 2004. This is Arctic sea ice extent, and you can see the Arctic sea ice extent is going down. So these are the observations shown on same observations on each of these graphs. And people are thinking that by 2050, during summer, the Arctic may be free of sea ice, which would mean a lot more transit from, say, South Korea, bringing cars into North America. It wouldn't have to go anywhere except right over the pole, a much shorter distance. The blue curves are the results of the sea ice extent in different models. And you see there are 12 different models here. Some models do a better job on the sea ice. Some models do a worse job on the sea ice. Sea ice, again, is a more difficult process to model. And I show this to indicate while models are generally in the right ballpark, they're definitely not perfect. Okay, how about reproducing past climates? Well, back in 1985, when we started modeling the Ice Age climate, there was an NSF committee put together to try to provide what the sea surface temperatures were for the last ice age. And one amazing result from that consideration was that the Pacific they had was actually warmer during the time period at high latitudes when you had big ice sheets covering New York City, right, at where we are right now. So we looked at that issue and tried to relate what the model would get when using those sea surface temperatures compared to land evidence of what happened at the time, such as glaciers coming down mountains in the tropics, or vegetation retreating up mountains, or vegetation coming down mountains because it was just too cold. And what we found is that it didn't work. You could not reproduce the land evidence by using those sea surface temperatures that we were given. So we made a big deal about it and said these two data sets are inconsistent. And given that we sort of understand how glaciers can really go down mountains and why vegetation will retreat when conditions are too cold, we sort of believed the land evidence. We thought that the ocean data was probably not right. The ocean data is developed by using proxies, forams and various other things that live in the ocean that have sort of a temperature sensitivity. Well, this was the IPCC simulation for in 2014 of the ice age temperature changes. And you can see that it's still warm in the tropics compared to high latitudes. So that was 30 years after we had pointed out that they don't seem to be right. And from this concept, you might think even by 2014, that problem still exists, potentially at least. I had a comment about paleoclimate problems, and that is they're never actually solved. People just get used to them. Well, what has happened since 2014 is people have started to take this problem seriously. And now there are a number of new papers, which I think will be integrated into the next IPCC report, that indicate how much colder the tropics really were. The difference is that if you use the assessment in the top picture, you get ice ages were about 3.5 degrees centigrade colder than today, which is certainly not all that much. Now I think the feeling is they were probably between 5.5 and 6 degrees colder. So one comment about assessing past climates using models, you have to actually know what that past climate was really like. One other problem I'll point out is you can see at the higher latitudes that you're getting very cold temperatures over North America and Northern Europe and Scandinavia. Those temperatures are cold because there are big ice sheets there. One other paleoclimate problem is how did the ice sheets actually get there? The general feeling is that it's the Earth's orbital variations around the sun that initiate the cooling, and then carbon dioxide gets reduced, and put it all together, you get the ice sheets to grow. Well, we tried to use our climate model to grow these ice sheets. And despite all the incentive we gave it, the orbital variations, the reduced carbon dioxide, changes in ocean circulation, it could not maintain those big ice sheets. The reason is, the thought is that in order to get ice sheets to grow, you have to have snow hang around through the summer season. The temperatures in northern Canada, or in these regions, reach 15 degrees centigrade in summer. We just could not get the model to reproduce that degree of cooling in order to get snow to hang around. The thinking right now is that maybe models can't do it because we don't have sophisticated ice sheet models. But this is another problem that exists in terms of understanding paleoclimate and use of our models to reproduce them. One follow-up comment is that the top picture raised the question of what is really the sensitivity of the tropics to climate change. If you really had an ice age climate and the tropics didn't cool much, you would say, well, they're pretty insensitive. The second picture on the bottom raises the question of How sensitive are high latitudes to climate change? If we can't get our models to cool sufficiently at high latitudes, maybe our models just are not sensitive enough. So we address this issue directly in looking at the question of how well do we know high and low latitude climate sensitivity? And we showed, as a function of latitude, doubled CO2 results from the GFDL model, which showed very little tropical warming and very great high latitude warming, and the GISS model, which showed more tropical warming and less high latitude warming. And even today, there are big discrepancies from one model to the next in terms of what is the sensitivity of high and low latitudes. Low latitudes, the thinking is the sensitivity is associated with cloud cover, which is pretty difficult to generate properly. High latitudes may have to do with sea ice response. We don't really know. So another indication that in terms of what we have in our toolkit for climate models still has a ways to go. Realize climate models are only about 50 years old, so they are basically a relatively new science. Eventually, we will sort of understand these processes better. Okay, so that was testing the models. How about building the models in the first place? Well, we don't know how all the processes work. We don't know exactly how clouds are generated or things like water infiltration of the soil when it rains. Some processes occur on scales that are too small to include in global models with the resolution they have now, like tornadoes. Turbulence, it's parameterized, but we can't do it from first principles. And we don't even know that well enough. There are a lack of observations for many aspects of the climate system used for evaluating the processes, like convective activity or how ice sheets move. And finally, as I'd mentioned earlier, the numerical schemes and the relevant equations are not perfect when you're dealing with models on these scales of 100 kilometers on a side. How about testing the models? Well, we saw what the test looked like when we looked at the global mean temperature over the 20th century. Here are the observed changes in the surface air temperature. And one of the things that's obvious is that high latitudes do tend to warm more than low latitudes. This blue region here, we will get back to as a slight cooling. Can models reproduce this effect? Well, actually pretty well. Models do get greater warming at high latitudes. Again, as I mentioned, the degree of warming at low latitudes does vary from model to model. So in this respect, models are not bad. You might ask the question, how well do we actually know what the surface temperature was back in 1901, especially over the oceans? And that does remain a cogent question. You know, it falls under the rubric of you don't know what you don't know. The bottom picture shows the observed change in annual precipitation over land between 1951 and 2010. The reason that it starts in 1951 is even the most egotistical of climate researchers cannot justify in their own mind the fact that we know what the precipitation was like over land back in 1901 in many regions. So we're just asking the question from 1951 through 2010. The changes are not very large. We don't have a great deal of confidence in them. And there's not a great deal of confidence in models' ability to generate them. Rainfall is hard to generate properly in models, and it's hard to observe. Now, in order to get these trends, either the global mean temperature trend or the local trends over the 20th century, the model will not do it by itself. It has to be given some reason for there to be a trend. And so that gets into how well can we force the models over this time period. Model forcing is thought of in terms of the radiation coming in, the energy in a watts per meter squared sense. And again, don't worry about a lot of these details. We'll talk about the four main climate forcings. One has to do with trace gases that man is putting in the atmosphere. And if this was a play, without a doubt, the main actor, the actor whose name would go before the title of the play or the movie, is carbon dioxide. Carbon dioxide increases, especially since 1950, are the prime forcing factor in terms of tending to warm our planet. But methane also tends to produce some degree of warming, and some of the other trace gases as well, a number of the more recent ones since 1950. But when you come right down to it, global warming is primarily a carbon dioxide problem. And if you look at the rate of change of this radiative forcing, you can see all of that, almost all of that changes since 1950. Another potential factor has to do with the sun's energy. We know that during sunspot cycles, the sun's energy goes up and down a little bit. We have measured the sun's energy, not with one satellite, but with a number of satellites since 1979. So we have a pretty good idea of what's happening in terms of solar energy. And there has been no explicit trend, though there are things that go up and down. Going back further in time, you can hypothesize that there was a long trend, but these curves represent different people's estimates of what happened back in the so-called Maunder minimum time frame. And you can see there are big differences in terms of what people think the sun was doing at that time. When you come right down to it, we don't have a good idea of what the sun has done prior to the time when we actually started measuring it, though there are some proxies that people use, especially for the 20th century. So these are two potential warming mechanisms. If you take the long time frame, sun has warmed, and greenhouse gases, the sun has warmed. Greenhouse gases, the climate has warmed. Again, greenhouse gases warm the climate by absorbing radiation coming from the Earth, whereas solar radiation obviously warms the climate by giving you radiation to the Earth. The two potential cooling mechanisms have to do with aerosols in the atmosphere, which are little particles of dust or liquid that are thrown into the atmosphere by a number of different processes. A common cooling one is sulfate. You get sulfate in the atmosphere, for example, when coal is burned and it emits sulfate to the atmosphere. A natural aerosol would be dust thrown into the atmosphere. These cool the climate by reflecting sunlight back out to space. Black carbon is an aerosol that warms the climate by absorbing radiation coming up from the Earth and maybe even a little of the sun's radiation. To understand the situation with tropospheric aerosols, this is a comment from IPCC 2013. The total aerosol effective radiative forcing due to interactions directly with radiation or interactions with clouds and radiation is between minus 1.9 and minus 0.1 watts per meter squared, with a best estimate right in the middle. If you look at what actually happened for carbon dioxide, its total radiative forcing over this whole time period was about 1.7 watts per meter squared. If aerosols cooled the climate by 1.9 watts per meter squared, it would have wiped out most of global warming. So probably it didn't do that. But we do not have a good idea of what the aerosol cooling has been over the 20th century. So that's a big problem when we try to force the climate system, not knowing what the biggest cooling mechanism was really doing. On another level, volcanic aerosols are dust particles or sulfur dioxide generated up in the stratosphere from volcanoes. And again, you can see different people's estimates of what volcanic aerosols have done. Big uncertainty there too, but not nearly of the same magnitude from a practical standpoint as tropospheric aerosols. Okay, finally, let's get to the scientific problem of predicting the future. Well, this is a different type of problem. In particular, we don't know what society will do to affect future releases of trace gases, or for that matter, of aerosols. So in the IPCC 2013 report, different respective scenarios were hypothesized. Representative concentration pathways, or RCP. And the number at the end relates to the watts per meter squared forcing they would be producing at a certain point in time. The low rate, the ordinate here is the equivalent CO2. So it's not exactly CO2 in the atmosphere, but it's the equivalent CO2 if you add the forcing from methane and CFCs and those other trace gases. So here you have 4 potential futures. And this was what was given to climate models to assess. Right now, for the latest IPCC report, there are the so-called SSPs, which are somewhat different in nature, but they're still different scenarios. So you have a low one, 2.6, and a high one, 8.5. The thought was, if mankind continues emitting trace gases, greenhouse gases to the atmosphere, maybe they'll follow the 8.5 route. If mankind is serious about eliminating these gases and the gaseous emissions, maybe we'll have the low route. The current view is that 8.5 is too much, that really there's no way we could actually get up to the equivalent of 1,200 parts per million carbon dioxide in a practical sense. However, this paper by Schwamm et al. Notes that up to 2020, we are actually on the pathway of RCP 8.5 relative to what these more modest assumptions were. Okay, so keep in mind these different guys. 8.5 is the high, 2.6 is the low. Most people thought that probably will end up somewhere between 4.5 and 6.0, which people thought of as a business as usual scenario. In other words, not really doing anything. This is an assessment that models produced of what the global surface temperature change would be like up through 2100 if we followed these different scenarios. And these different bars here indicate what the different models, the range of global warming the models got for the different scenarios. Now, to put it in perspective, the Paris Accord said we should definitely keep global warming less than 2 degrees centigrade by 2100, but it would be preferable if we kept it less than 1.5 degrees centigrade. Now, recognize that we were already at 1.1 degrees centigrade relative to pre-industrial terms. So to keep it less than 1.5 means that we'd have to have the rest of the warming up through the year 2100, or at least 2050, be the same amount of warming that we've actually gotten from 1970 to the present, or actually from 2000 to the present. In any event, so these are the temperature ranges you can think about. RCP 8.5 would give a 4-degree global warming. RCP 2.6 would give a 1-degree global warming. And to get 1.5 would be somewhere around RCP 4.5. One other thing I'll point out is, remember that blue picture we saw, the little blue in the North Atlantic, about what has happened to temperatures since 1900? You can see some of the models for these different scenarios do reproduce that. And we did an extensive attempt to understand what was going on. This has to do, at least in our models, with a reduction in the North Atlantic circulation, the overturning circulation. People believe that ocean circulation is quite sensitive, and it's possible that as climate continues to warm, that circulation will be reduced and maybe even shut down, which will affect things like the Gulf Stream location, have its own impact on coastal temperatures in Western Europe to some degree, fish location, things of that nature. Okay. What else would you like to know about the future? Well, probably the primary component that global warming has a chance of influencing is water availability. And this is an IPCC result for the soil moisture change in the latter part of the 21st century for RCP 2.6, 4.5, 6.0, and 8.5. The thing to note is that by the time you get up to 4-degree warming, you're drying out North America, South America, Western Europe, South Africa. These are from models soil moisture, near surface soil moisture. The hash lines indicate regions where the models just did not agree, and the disagreement was greater than the changes they were producing. Models have very difficult time getting soil moisture correct. For one thing, it's hard to see what the current soil moisture is. It varies so much from place to place. And so models can't test their soil moisture very well. And also, soil moisture is, again, part of the hydrologic cycle that models have some problems with. In addition, one of the things you may know is that there are drought indices that the National Weather Service produces during summer, which says, oh, well, this drought index shows that it's very dry in California or the Southeast US. We applied the drought indices to our climate model output. And the drought indices, this is what you get with 4-degree warming, showing wide, extensive droughts over a good deal of the northern and southern land areas that today occur only 1 in 100 years. The drought indices show much more extreme problems with soil moisture than the soil moisture itself does in models. So that's another issue to be concerned about, whether the extremes that one gets with global warming may be underestimated. I would say also, in either of these aspects, 4-degree, either the soil moisture or the drought index, you can see how much worse 4-degree warming is than 1-degree warming, or even than 2 degrees warming. At the rate we're going now, if you just assume that what we've been seeing over the last couple of decades is what will continue, we will be above 2-degree global warming by the year 2050. And there is a good chance we will be above 3-degree warming by the year 2100, which puts us somewhere in between these two extremes. Okay, a few more questions about the future. People are quite interested in what will happen to agricultural yields in 2050. And this is for RCP 6.0, which I think we saw was about a 2.5-degree global warming. You see the percentage change relative to today in production. And this line is the 20% line. For most of these species, wheat, rice, corn, soybeans, you get something around a 10 to 20% reduction, depending upon the particular model that's used to estimate it, either the agricultural model or the climate model. Sugar actually thrives in many regions because it likes warm, moist climates. A big uncertainty here is that it's widely recognized that when you have higher carbon dioxide in the atmosphere, plants like it because they don't have to open their stomates so much to take in carbon dioxide, and therefore they don't lose as much moisture to the atmosphere. So they stay more moist. And their temperature can be better regulated. The problem is we don't actually know how well CO2 fertilization works in the real world. It works, the ability to grow better with more CO2. It works well in laboratories, but the real world, there are many other potential problems: pests, temperatures, nitrogen availability. So if you did not have CO2 fertilization in this picture, you would be getting decreases between 20 and 40%. And then you'd have real questions as to whether the amount of people expected to exist in 2050 and after would be able to be fed on this planet. Finally, the last question for the future that we'll discuss has to do with sea level. During the 20th century, sea level rose about 18 centimeters, which would be this 0.18 on this global mean sea level rise picture. Here are the estimates for these different RCP scenarios for what sea level would be like in the year 2100. Note for the RCP 8.5, at this point, it had sea level rise of 70 centimeters compared to the 18 centimeters that happened last century. However, people have noticed that there's been a lot more melting of Greenland and Antarctica than they anticipated. In fact, in the 1990s, melting of Greenland and Antarctica contributed about 5% to the total sea level rise. Now it's contributing about 30%. So the latest estimates for sea level rise now, the mean value is 70 centimeters by the year 2100. But the big uncertainty, the 500-pound gorilla in the room is what's actually going to really happen to Greenland and Antarctica. Greenland has enough ice that if it all melted, it would raise sea level about 7 meters. West Antarctic ice sheet, the most sensitive component of Antarctica, could raise sea level about 3.5 meters. Nobody really believes these ice sheets will completely decay away during the 21st century, but I can tell you that earlier IPCC reports said absolutely not, very little chance whatsoever that there'd be great desiccation of these ice sheets by 2100. The latest IPCC report says, well, we don't think there will be great desiccation. You can tell from the fact that the language has become a lot less certain that people are getting more and more worried as to what would actually happen to these ice sheets. By the way, I can give you an anecdote that's sort of relevant to City College a little bit. As you probably know, Columbia University is doing a lot of building near the Hudson River, extending up from 120th Street to 140th Street, at least. And if there's any degree of desiccation of Greenland and West Antarctica, the region that they're building in will become very, very vulnerable to sea level rise and the rise of the Hudson. And one of my colleagues, Vivian Gornitz, has published a report saying that this region should not be built upon. That report is actually on, she's a Columbia University employee, and it's actually on the Columbia University website. So I asked her, how come Columbia is going full bore in building in these regions that you yourself pointed out are very vulnerable? And she said, I have no idea. It's on their website. They could look and see. And it's not only her projection, it's other people's projections as well. So it's not necessarily a doomsday scenario. Maybe it will be 70 centimeters, which will not be nothing. It will certainly cause greater inundation in certain regions of the New York City area, and even more so if you get tropical storms come anywhere nearby. But there is the potential for much more catastrophic sea level rises. Okay, so we went through what it takes to build a climate model, how you test the climate model, and what problems arise in building climate models and testing them. Now let's get more to the question of education and what it takes to specialize in and build climate models. So I've listed here disciplines that are involved in the climate model research area. Well, if you really want to know how the sun's radiation has changed with time, solar physics, absorption of radiation by the atmosphere, especially radiation coming up from the Earth, atmospheric radiation, clouds, cloud physics, aerosols, aerosol physics, the movement of the atmosphere, atmospheric dynamics and meteorology, all the rainfall and evaporation processes, hydrologic studies, climatology and past climates, paleoclimatology. Ozone is itself a gas that affects radiation, and so atmospheric chemistry to understand how ozone has varied due to CFCs and other things. and atmospheric chemistry in general. These are run on computers, numerical modeling. You have vegetation that you have to have in the model. It has to grow, it has to take moisture on its canopy, it has to wilt if things get too dry, vegetation dynamics. The water goes into the soil, energy goes into the soil physics and ground hydrology. If you want to be able to predict what the carbon will be in the atmosphere for given atmospheric emissions, a carbon cycle in the atmosphere and ocean. The oceans have their own model, they move around. The Gulf Stream is an example of that, ocean dynamics and ocean chemistry. Sea ice moves around, sea ice may disappear in summer over the Arctic, sea ice dynamics and thermodynamics. Big uncertainty with land ice models, both for Greenland and Antarctica, and also for the last glacial maximum, land ice dynamics. Using satellites to understand what's happening in different parts of the atmosphere and different parts of the climate system, remote sensing. And then the whole aspect of climate change impacts on health, water availability, sea level, natural and managed ecosystems, economics, energy, demographics, foreign policy. Another little anecdote, many years ago, I went with Jim Hansen to the Defense Department to try to make the case that global warming is going to have a strong impact on where people live. And there'll be a lot of movements which will upset foreign policy, which will lead to potential wars over rivers. And what we were trying to do was to get the Defense Department to put a lot more money into climate modeling. Well, it didn't work. But we now understand they were taking it seriously, and they do take it seriously. They were just keeping everything in-house. Okay, so we went through the scientific problems, but climate modeling is more than scientific issues. It involves, obviously, humans. So in practice, how does this work with all of these different disciplines involved? It's impossible for any one person to understand all these wide-ranging disciplines. So one must work in a team with others. Learning to coordinate work with researchers from other fields is not easy. There's different terminology, there's different underlying philosophy, there are different practical approaches. In each sub-discipline, like, for example, vegetation dynamics, there's a balance between the complexity of the subject and its sophistication and the computer time required with respect to all other parts of the model. These models have to run hundreds of years. You can't spend all your time on the shapes of the leaves in trees. That's a problem, because when somebody is spending a lot of time trying to understand their subdiscipline, they don't want to see climate modelers come along and parameterize it in a few lines of code. So this is a human problem as well as a scientific problem, each of these different components. Management is of prime importance in this enterprise. You have to get different people to work together, you have to coordinate it, you have to sort of ease it into existence. And unfortunately, scientists are generally not trained as managers. So again, without mentioning any names, I have seen varying wide degrees of capability of managers of climate modeling processes. Okay, finally, what does this mean for student education in the field of climate and climate change and climate modeling? Obviously, students also cannot be expected to be familiar with all these different fields. It would be useful if students were to learn something about a number of these different areas. But how are they going to do that? Departments are often not set up for interdisciplinary studies, even within the sciences, which this field requires, let alone climate impacts. Also, there is the threat of becoming jack of all trades, master of none, if one tries for too much breadth at the expense of depth. Thus, practically speaking, one must become knowledgeable with depth in at least one of these core areas. And that can be sufficient for a successful career in this field. You become known as the cloud guy, the cloud physics guy, for example. And you can get a job in places that need a cloud physics person. Often students are advised to specialize in physics and math, thinking that preparation will leave them in good stead for any subsequent work in a physical sciences field. However, we're dealing with an applied physics field having to do with the real world. And my experience is that one needs to develop a feel for the discipline in which one will actually work. Physics and math are necessary backgrounds, but they're not sufficient. In my case, taking all the meteorology courses at CCNY allowed me to have a feel for the atmosphere. Frankly, something my colleagues often did not. They came from either numerical modeling background or a physics background. So when things were happening in the model, they just assumed that, well, energy was conserved, so it must be okay. And yet, if you have a background in meteorology, you know things just don't happen that way. I thus had some insight as to whether things were working for the right reason. Some knowledge of other relevant disciplines can be obtained by actually working in the field. I mean, you're in meetings and somebody who works on sea ice modeling discusses some of the problems in sea ice modeling and what needs to be done. And so you learn that way. And you can attend meetings. There are meetings, sea ice meetings, land ice meetings. You can read articles yourself. So it doesn't all have to be done as a student. But it's useful when you're working in the field to become flexible enough to explore these different areas. And I say, excelling in climate modeling is enabled by being flexible enough to explore beyond the confines of one's subject. And for me, this approach also has led to a much more interesting experience. Now, the last couple slides are just suggestions. I don't know if anybody at this school has interacted with the EdGCM project. I've given the website for it. And a colleague has developed a research grade global climate model with a user-friendly interface that can be run on desktop computers. Students can explore the subject of climate change and, in a way, climate modeling in the same way research scientists do. As you can see from the rest of this slide, it makes possible for people to use the GCM without requiring program skills or supercomputers. And there's a graphical interface, a searchable database, scientific visualization software, an e-journal for reports. It comes with 6 ready-to-run climate model experiments, 2 modern climate, 3 global warming simulations, and 1 ice age simulation. It has been used there. You can download it. There is a cost to it. You can download it from that website. There have been more than 50,000 downloads. There are 150 institutions, undergraduate primarily, and some high schools that are already using a GCM. It's been used successfully in science competitions. So I just mentioned this. And then the last thing of mention is that NASA actually has a limited number of internship opportunities for high school, undergraduate, and graduate students who reside within a 50-mile radius of GIS, which is on the Upper West Side. Interested students should apply at the intern.nasa.gov website. And noted that you have to be US citizens, New York City area residents, and have a formal education program of study with a minimum grade point average of 3.0. So thank you for listening to this. I have to say that my time at City College was greatly enjoyable. I loved being in the meteorology department there. I learned an awful lot about weather, about the atmosphere, about meteorology, about the upper atmosphere, about all sorts of things that definitely set me in good stead for what I then had to do in my work subsequently, and also helped provoke interest in the field, which is sort of the bottom line for any activity you go into. You're going to be spending a lot of time doing it. You should be interested in it. And City College was definitely a major component of developing my interest in this field. Thank you.
Thank you so much, David. That was wonderful, and I loved how you ended off with those inspirational words to our current students. That was great. For those of you in attendance, I've said it a couple times in the chat. If you have a question, please type it into the Q&A box. We're going to do a few of these questions, and then we'll present Dr. Rind with the award. There actually is an award. It made it on Monday during the blizzard. So we'll take a few questions and then we'll pause and we'll wrap up before 5:30. I know folks have children and plans and other events, but I did see some questions coming in. I'm going to turn it over to my colleague, Dr. Johnny Luo, to pose them.
David, that's a wonderful talk. Enjoyed it very much. It brought me back to my graduate years. Yeah, I will start from a general question, then a more specific. General one is that says that if you had a magic wand, what should be the single most important thing that you would do to mitigate climate catastrophe?
Well, ultimately, the thing about magic wands is they can do something that we can't actually do. The reason CO2 is such a big problem, and people know it's such a big problem, is because all our transportation emits carbon dioxide, but more important, our energy production to a good extent, fossil fuel burning, emits carbon dioxide. If we could wave a magic wand, we would come up with another energy source that could replace carbon dioxide without having its own problems. As we know, people are developing solar energy, in particular the batteries that will enable us to maintain the energy received from the sun and store it. There's wind energy, there's geothermal energy, and there's nuclear energy. Nuclear energy is the only one at this point in time that can replace fossil fuel burning for the energy resources that this society needs and that will need in a growing fashion in the future. But as we know, nuclear energy has its own problems. What do you do with the waste products developed by nuclear energy? What do you do so that you don't have another Chernobyl event happen that will affect millions of people, basically? So if I had a magic wand, I guess what I would do is I would have fusion energy work. Fusion energy makes use of, it's how the sun works to generate energy as opposed to the fission energy that our nuclear reactors work on now. People have been, I can give you an anecdote. In the year 1990, Time magazine had an estimate of what the energy usage would be in the year 2050. And for fusion energy, they had 0%. So I was at a meeting of fusion energy researchers at Georgia Tech. And that morning I had breakfast with them. And I said, you know, we're 10 years later now. 1990, Time magazine said there would be 0% fusion energy contribution to our energy needs in 2050. What do you think now, 10 years later? And they said, still 0%. Because they said, all they have is theories, ideas of how it would work. You have to contain a 10 million degree hydromagnetic fluid. And until we actually build these instruments and try them out, we have no idea whether any of these theories will actually work. They said that in order to build a full scale, this was in $2,000, a full scale fusion reactor, it would cost $28 billion. And they said no government is willing to do it because they said that should be the private industry should do it. They said even a small scale one, which would cost 16 billion, they can't get funding for that. Well, in the meanwhile, since then, governments have now decided that fusion energy is something they should look into. And they are building a small scale fusion reactor with the hope that eventually they would build a bigger one. The bigger one was supposed to be built in Japan. But since what happened in Japan with earthquakes and their own nuclear catastrophe there, who knows what's going to happen. So if I had a magic wand, what I would have done was back in 1990, or maybe even 1970, I would have devoted a lot of resources to try to build a fusion reactor that could supplement and ultimately replace the use of fossil fuels for energy. And the waste product from fusion reactors is water vapor. So it wouldn't have the same problems that fission reactors have now.
Wow, that's very nice. Well, I guess we have to build a time machine to go back to 1970 to do that. Suzanne, how much time do we have for questions, or we're running out of time?
I think we can squeeze in one or two more. So
okay, so yeah, there are a lot of questions that have to be selective. Some of them ask about details about modeling. One question is about NASA GISS model. Besides higher spatial resolution, were some of the other major drivers for being able to better simulate the Pacific storm track, the one you showed earlier?
Well, it's not so obvious because a lot of things are interrelated. For example, if you have the cloud cover incorrect in the tropical Pacific, then you will not be warming and generating upwelling motion properly in the Pacific. And therefore, if you don't have it going up at the right location, it will come down in the wrong location. And we know that when air subsides and warms, it tends to generate higher pressure, which prevents the storm tracks from going far enough south. So ultimately, I think when you come right down to it, the real problem with the storm tracks in the North Pacific has to do with cloud cover in the tropics. People recognize that cloud cover in the tropics is a big issue. If you remember, I noted that in terms of the model biases for surface air temperature, the tropical oceans in the Atlantic and particularly the Eastern Pacific tend to be too warm. It's because the marine stratus and stratocumulus clouds cannot be generated properly in that region, and too much sunlight gets in and warms up that region. And again, with a warm region there and rising air, you will get subsidence further north in the North Pacific, which will extend the high pressure regions too far north and keep the storm tracks away. So I don't actually think it's a dynamics issue. I think it actually ultimately is a cloud cover issue. But that's indicative of how all these problems in the models tend to be related. And you ultimately have to develop a more holistic point of view of the system to try to figure out what's going on.
Excellent. We have about 7 minutes left before 5:30. Suzanne, how do you want to proceed?
Why don't you choose one more of these questions and then we'll
okay. Actually, my own PhD student, she asked the question about generally the philosophy about building model. Would it be beneficial to have a model that's slightly too simple, or you want to have more complex but not well understood details into the model? What's your thinking on that?
Well, so one thing that people often do in physics is that they do a scale analysis of the problem. And they said, oh, well, we have these 4 components that are potential contributors to the experiment. And we note that 3 of them are of a pretty large order of magnitude. And the 4th guy is pretty small. So we'll remove the 4th guy from our consideration and deal with these other 3. In effect, that's often how simpler models are built, by leaving out the smaller component. The problem with doing that, especially in climate models and in the atmosphere itself, actually, is that many times these models have forces that work against one another and are approximately of the same order of magnitude. And it's the little guys that determine what ultimately happens. I think of it as sort of like a catalyst in a chemical equation. The catalyst is a very small component, but without the catalyst, the reaction doesn't actually happen. And there are many studies, for example, of Hadley cell sensitivity or jet stream sensitivity, in which people just ignore the smaller components, thinking that they're not important. Now, in the climate system, it's the same sort of thing. you may have things like cloud cover and its potential effect on the system. And if it's difficult, you just sort of ignore it. There are models, so-called models of intermediate complexity, that make certain assumptions about how transports in the atmosphere will vary as the more resolved parameters in the model vary. And we have done studies in which we have looked at what actually happens in our model when you include all the other components, and those assumptions just fail to verify. And I'll say one last thing. One thing that's often used in atmospheric dynamics is quasi-geostrophic theory. And without going into great detail, it sort of linearizes these dynamic equations. I don't know if Johnny, if you ever knew Walter Robinson.
Yes.
So Walter Robinson, for his thesis, built a quasi-geostrophic model, which made the same assumptions on scale analysis and got rid of the nonlinear components so that you could have a simpler model. And we did experiments in which we did the exact same forcing of the quasi-geostrophic model and of the full climate model to understand sort of dynamic issues. And what happened was that what you expected from the quasi-geostrophic model from that forcing, based on quasi-geostrophic theory, is exactly what that model did. It perfectly replicated what the theory expected. But the climate model, or in fact, the general circulation model, did not do that. It was considerably different. So his PhD thesis was about building a quasi-geostrophic model and the concerns one actually has in using it under these various circumstances.
Excellent. Thanks for the insight. Very helpful.
Great.
Suzanne,
I'm gonna just offer, so Dr. Zhang, the chair of EAS, just put in the chat, there is a meet and greet tomorrow with Dr. Rind, which is not webinar format. You can actually see each other's faces. So if you are interested in following up with some other questions, please email him. We also will download the questions, and so we'll try to get them answered. Perhaps we can do some other posts, or I can put them when we post the video.
I mean, if somebody just sends questions, I can respond to them, you know, type out responses and so on. So
okay, that sounds great. Maybe we'll do that, and like I said, I can post them in the comments. But
yeah.
But now I think it's time for you to open this box that's been.
Okay, so I got this box which survived the snowstorm to get here.
Amazing.
The people in my building were actually quite astonished that something showed up because they had heard that packages weren't being delivered.
Yeah, so there's a plus for UPS. So we're very happy to be able to.
So I have a pair of scissors here.
It's just a token of our appreciation. We're so grateful that you could share in this today. It was a really insightful, wonderful talk. I learned a lot. This is not at all my field.
Thank you.
This is all new to me.
So here's a box that was in the other box. And I'm in the process of opening the box.
I see that it's been packed well. This brings me
very well packed.
Definitely brings me comfort.
It said on the box, open immediately in case things are broken. And here is the wonderful award.
That's great. Maybe put it in front of your chest and then the video will, there you go.
And it says on it, for elevating the City College through your significant accomplishments and professional service, the Division of Science at the City College of New York recognizes me as a distinguished alumni. Thank you. By the way, it was noted that I included the Ward Medal on my CV. I did not do it just for this particular presentation. It's been on the CV all these years.
Excellent. Well, now you have a new addition to your CV. You'll have to update it tomorrow. So
okay, thank you.
Your honors. Congratulations again on behalf of everybody in the Division of Science. You know, you've made City College very proud to consider you amongst our family. I can't wait till we can do this in person. You know, I wish we were wrapping up and heading over for a celebratory dinner with you, but we will make it up to you. You're a New Yorker, so we've got lots of opportunities. So as soon as it's safe to have you come back up to campus, we'll do it again in person and congratulate you properly. But
Thank you. It will be my pleasure. And thank you again so much for this award. It means so much.
oh, we're so pleased. I want to thank everybody who participated today. It was really lovely to see the participants. I love scrolling through, seeing who's here. And I put in the chat, we have our third presentation, Dr. Carol Mendelsohn. So she's from the Department of Biology. And I put a link there. We'll be circulating that information as well. That will happen on March 4th. And I hope you can join us as well for her talk. So thanks again, everybody. Congratulations again, David.
Thank you.
And I hope everybody has a wonderful evening, and we'll wish you luck tomorrow at the meet and greet too.
Thank you. And good luck on your your next meeting.
Well, and Carol was in the audience, so she now has a good role model to know how to do this. So,
Okay.
All right, good night, everybody. I just know when I hit end, the whole thing shuts down. So there's no green room here. All right, take care, everybody.
Bye.
We'll see you soon.